Yeah.
Okay, I think we should start. So welcome everybody to session 6C. And our first speaker is Philip Wellnitz, and he will give the first talk. Philip, please.
Thanks, Shai, for the introduction. This joint work with Panagiotis Charalabopoulos and Tomas Kotimaka. And as the title says, this is about pattern matching. So let's quickly recall pattern matching problem. Well, as you all know, we're given a text T and a pattern P. We are to find all occurrences of the pattern in the text. So for instance, there's exactly one cake and pancake. But most of the time, like exact matches are not good enough, right? Think of spelling mistakes in the text for the pattern or noisy data. So that's why we consider approximate pattern matching. What do I mean with that? Like the first thing we consider is pattern matching with mismatches. So here we search for all occurrences of the pattern that have up to k mismatches. So for instance, if you allow for up to 2 mismatches, then you can find unpun in pancake. Now mismatches are like rather restrictive. For instance, they don't cover like surplus characters or missing characters in a text or a pattern. So we also look at pattern matching with errors. So here we're searching for starting positions such that pattern when aligned to this position has an added distance of at most k. So for instance, if you align plank at the first position of pancake, allow for up to 2 errors, then this is also a match. And one setting that we are especially interested in is when both text and pattern are given in a compressed representation. So think of huge data you want to compress, right? And so ideally we'd want to work with these compressed data directly. That is without decompressing it first. But first, let me quickly mention what I mean with compressed data. Particularly, we look at grammar compressed data, just to say that we are given just context-free grammar that generates exactly one string. Okay. So to illustrate what is known, let me recall some flagship results. So for the uncompressed setting, I guess we're all aware of classical linear time algorithm for exact pattern matching. Quite surprisingly, Yesh showed 2015 that also for the fully compressed setting, that is where both text and pattern are given as an SLP, can do so in linear time in the compressed size of text and pattern. And this totally here hides some logarithmic factors in the uncompressed length, though. Okay, so for exact pattern matching, the situation is pretty good so far. However, for approximate pattern matching, it's not as good. So while we again have like roughly linear time algorithms for the uncompressed setting, for the fully compressed setting, essentially nothing was known. The best thing or thing that comes closest is perhaps an algorithm by co-authors and myself, where we something that worked with compressed texts but uncompressed patterns. There we got something roughly linear. And again, this only worked for uncompressed patterns. And for pattern matching with errors, the situation is even worse. Again, we have a roughly linear time algorithm for the uncompressed setting, but for the fully compressed setting, only quadratic time algorithm was known, and then there's some polynomial dependency on k only. So what we do in this work, among other things, is that we fix this picture by providing roughly or almost linear time algorithms for both approximate pattern matching settings. And in fact, our algorithms, like, they're rather general, so they also give alternative algorithms for the uncompressed settings that match some of the fastest known algorithms there. Okay. So how do we obtain these results? So in one sentence, we obtain these things or these new results by improvements in the solution structure, or by improvements in the insights in the solution structure. So what do I mean with that? Well, let me quickly recall what was known about the solution structure only for pattern matching with, or here only results for pattern matching with mismatches were known, but let me quickly recall them. So co-authors and I showed that for a pattern and a text, one of the following things is true. either we have only k-squared k-mismatch occurrences, or the pattern is almost periodic already. Okay, and then there's some additional insights into the almost periodic case, which I'll skip for now. So, and now if you look at this theorem, it may, may already see that it's not really or may not look optimal to you. And in fact, we can show that, or we can tighten this in the following sense. This is what we did in this work. So first of all, we showed that the number of k mismatch occurrences is only linear in k. And also we tightened what it means to be almost periodic. Okay. And now, of course, you may ask, are these bounds now finally optimal? And indeed they are, but I'll defer to the long version of this, or long video for this paper to see the details. Instead, let me quickly glance over what happens for pattern matching with errors. Well, here essentially the same thing happens. The only difference now is that we again get order of k-squared occurrences. But now in this case, this is optimal because what we in fact can show is that these are order of k intervals of length, order of k each. And this then is, then we can show or give an example where this is tight. Okay. But let me focus on the Hamming distance, because essentially all of our proofs generalize to the edit distance. It was not the case for most of the, or for the work that I mentioned earlier. Okay. So let me spend some time on how we, or on the techniques. So the key lemma for achieving our main result is the following. So we show that for each string P, at least one of the following is true. So either the string P has 2k disjoint breaks, where break is a long part of the string, which is non-periodic, or alternatively, P has disjoint repetitive regions with a total length that covers like constant fraction of the text. And each repetitive region for itself looks like almost periodic. Or the third case is that the string was almost periodic to begin with. And now you can quite easily see that this key lemma implies the main structural theorem. Also, the proof of the key lemma is rather nice. It has a cool algorithmic proof. Consider or check out the long version if you are interested in details here. Instead of giving you some details, let me quickly mention how we turn these insights into algorithms. So the first thing that we observe is that all of our algorithms rely only on these 6 essential operations. And if you're working with strings, then these all kind of look familiar to you, I would say. And in fact, they're so essential that we call model computing stuff with these things, like we call it pillar model. And now how do we use this pillar model? Well, first of all, in this work, we provide fast pillar model algorithms, like algorithms only using these 6 basic operations. And then for free settings, by combining essentially known work, we can obtain fast implementations for all of these 6 operations. And then in total, we get fast algorithms. So as an example, let me give you the detailed results for the fully compressed setting. Again, quickly recall, here we're given a text as and the pattern as an SLP. And now what we can do here is we can use Yesh's recompression technique. Then we can implement all of these operations in log cube time in the size of the uncompressed text and pattern after some preprocessing. Then plugging this into our pillar model algorithms, we then obtain these 2 results. Just focus on the running times for now. Then you see that they're roughly linear in compressed sizes. Then there are some logarithmic dependencies, and then there's a k squared and a k to the 4th. And these essentially correspond to the same or similar running times also you have in the uncompressed setting. Okay, that's already. Thanks for watching till the end. And yeah, if you have any questions, feel free to ask.
Thank you very much, Philip. We're open to take a few questions. So check the Slack. Philip, can you say anything about the dependency on K?
Yeah, like I mean, like for pattern matching with mismatches, K squared, right?
Is that known to be optimal?
I mean,
even in the uncompressed.
I mean, in the uncompressed setting, like I mean, I showed you earlier this the slide here. Like there's a similar result with this running time, and then like if you trade with the parameters somewhat, then you get the second result here, and the second result has a matching conditional lower bound. So in general, there's perhaps not that much to be done. For pattern matching with K errors, this K to the 4 is, I would say, not optimal. Like there's a lower bound, or the general edit distance computing lower bound by Piotr and Indik gives you K squared lower bound, right? And like, I mean, like this algorithm by Cole and Harry Haran here, I mean, even they conjectured that it should be K cubed. And yeah, I think at least K cubed should be attainable. Like this is what I mean, like this K to the 4 is perhaps not optimal. Yeah, but also for our proof, still in some cases still need K to the 4 time. But perhaps this will be improved in the future.
Okay, thank you. Any other questions? Okay, thank you, Philip. If you can stop sharing your screen, and
okay,
we'll start the next talk in 2 minutes. Negev, you can, in the meanwhile, we can start sharing your screen.
Is it working?
Yeah, we see it properly, and we can see you. Yeah, we'll wait 1 more minute, and then we'll start.
So Ivor is the speaker for the talk after me, the 5th talk.
Okay.
He arrived.
Excellent. Okay, I think we can start. So our second talk will be given by Negev Shekel-Nozatsky. Negev, please.
Thank you very much. I'm going to talk today about how to approximate the eddy distance up to a constant factor in a linear time. It's a joint work with Alexander and Doni. Oh, good. So the eddy distance problem, one is given 2 n-length strings, and the goal is to calculate the minimum number of insertion, deletions, and substitution to transform one string into another. Computing the eddy distance between 2 strings is a very classic dynamic programming with known quadratic bounds from 74 by Wagner and Fisher. And the main question is, can one do better than the classic quadratic time? So there has been little improvement over the years, a lot of work. 6 years later, there was polylogarithmic improvement. And there was a long line of work that show better than quadratic in special cases. And more recently, a few years ago, it was shown that near quadratic time is likely the best possible if you believe at least in the strong exponential time hypothesis. So the question is, what about approximate? And here as well, there was a long line of work that showed polynomial approximation, and 10 years ago, roughly polylogarithmic approximation in near linear time. And the question is, can we do better than polylogarithmic approximation? And there was a breakthrough 2 years ago to show a subquadratic time for constant approximation, first for quantum time, and then for regular computational time. And the question is, what is the best runtime? Can we obtain near linear time also for constant approximation for the eddy distance? And there were 2 independent work that made progress in that direction earlier this year that show this is indeed possible for the far distance regime, meaning if the pairs are almost linear themselves, or alternatively, if one can afford the very large additive errors. And the question remains, what about arbitrary input strings? And in this work, we conclude that indeed one can compute the distance between any pair of input string in a near linear time up to a constant factor. And the approach is that basically we do alignment over substrings. So we define the xi and yj, which are substrings starting at position I and j in the string, and the substring are of some fixed length w. And it's not so hard to show that the eddy distance between the 2 strings is minimum over the optimal alignment for eddy distance of size w over all position, normalized by this size w. So this is how it works. What we're trying to do is we're trying to find the near optimal alignment pi between i's and j's using calls to substring comparison, where the substring of some length w. Okay, so this is the setting. And let's talk a bit about prior approaches. And what did they do to obtain the subquadratic time? The high-level idea, they have 2 high-level ideas. One of them is to use triangle inequality, and the other is to use some alignment properties to show that one can reduce the number of interval comparison. The interval is simply, we call the substring of length w an interval. And indeed, this helped them. And the alignment properties, what I mean is that for nearby i's and j's, well, over the x-axis, also pi of I and pi of j will be nearby, right? So we expect nearby elements to appear nearby in both axes. The way they're going to compare substring, all the work until now basically recurs on smaller instances in order to compare the w length intervals. And using recursion is very expensive. In fact, one cannot recurse on all sets of intervals, all n sets of intervals. It's not even allow you to use a single comparison to interval. So to avoid that, what they did is they only consider some intervals, ones that are roughly multiples of w. And this gave them, to do that, this must result in large additive error, because obviously the alignment, the function pi might not be exactly between intervals of exactly multiples of w. And you can play with it and get better runtime with, less additive error with more runtime and vice versa. And another thing that some of the work did is sometimes it's hard to identify certain number of pairs that have low frequency and are very sparse. So they avoided identifying some inconvenient pairs. So they only look for some interval, and they were able to ignore some of them. And this cost in additive errors with runtime trade-offs. To bypass this problem, I'm going to discuss now about what our approach was. Our approach, instead of recursion, we took more of a dynamic programming approach. So instead of starting with size and interval and then recurse to smaller and smaller sizes, we did the other way around. We started with size 1 substrings, length 1 substring, and then we make the size slightly larger each time until we can approximate n length substrings. And each time we build a distance oracle, d sub w for the metric of all intervals, right? All to n substring of length w, and something that is approximately their eddy distance. So here's how it works. The first distance oracle is very simple. You can use hashing or just use the Hamming distance on sigma, which is simply 0, 1, and you get the distance oracle for size 1 interval. And each time we use the previous distance oracle to build another distance oracle, until eventually we build a distance oracle for substring of length n of the entire string. And then we simply output the distance between the n length substring of x1 and y1, which is simply the distance between the entire strings. So the properties that we guarantee for this distance oracle is that this distance oracle with probability 1 always output an upper bound for any pair of intervals. And it's also a constant approximation, but not for any pair, but only on average for any alignment. And also consequentially also for the optimal alignment. So for any alignment, we show that this distance oracle will output the right amount on average and always an upper bound. And the other thing we guarantee is for any length w, we can do this in much faster than even linear time. We do it in n to the epsilon time, even for very large w's. So for any w, this distance oracle takes n to the epsilon time. So the new goal becomes, well, given a distance oracle for a substring of length w over n to the epsilon, well, let's compute the new distance oracle in near linear time. So how do we do that? Well, in high level, we have two components for algorithm. The first one is we build another oracle, another distance oracle, which is called the alignment distance oracle. The alignment distance oracle allows us to compare two substrings of length w using a distance oracle to substring of slightly smaller lengths of size w over n to the epsilon. And the guarantee here, and you can see the common theme is, it's not always a constant approximation, it's always an upper bound, and it's a constant approximation on average for any alignment. So this is only true for alignment. If things are not in the alignment, they might be completely off, and it will be on average true for every alignment. And here the main challenge is not just to guarantee correctness, but also triangle inequality, because we use triangle inequality in every part of our analysis. So we want to create a new metric. This distance oracle, alignment distance oracle, also need to preserve being something very close to a metric. And more importantly, we not just want to, we want to create a metric for this substring of length w. So we want to create a representation for the entire metric, and we want to do it in near linear time. So we need to find a sparse representation, and the sparse representation that we choose is a sparse graph, G sub w, and we're going to use this alignment distance oracle calls to L sub w in order to generate this sparse representation. And this is how it works. We have a matching algorithm that basically builds this graph, G sub w, that I don't have time to explain exactly how it works, because I'll give it at very high level. And the guarantee for this graph, G sub w, again, is that it's always output the distance in the graph. It's a weighted graph. It's always an upper bound for every pair of interval. And again, it's a constant approximation on average for every alignment, and also for the optimal alignment. And once we build this graph G sub w, well, then we simply use a distance oracle data structure. And the only thing we need is again, we need to guarantee both correctness and triangle inequality. And therefore, we cannot use any distance oracle that just guarantee correctness. But we need to use one that preserves triangle inequality. And again, we use an embedding to L infinity norm with dimension n to the epsilon. In this way, we preserve both correctness and triangle inequality. Just in 1 minute, the way we do this matching algorithm is to iteratively partition the set of 2n interval into smaller and smaller parts until they are small enough to be the exact density of such interval, and then we can cluster them in the graph. And how do we cluster them? We plant a star between one of the cluster and everyone else. So this star is very sparse, and it provides a 2-hop guarantee between all the xi's and the y pi i's that we need in order to do a constant approximation for the eddy distance. To summarize, indeed, one can compute the eddy distance after a constant factor in nonlinear time for any pair of input streams. The approximation is roughly doubly exponential in 1 to the epsilon. I don't have time to cover all the open questions, but I think the most interesting one are the last two. First, can one do better than 3 approximation? And for that, one would need to go beyond triangle inequality. And I think the other most interesting open question is, what about nearest neighbor search, where the difference between the lower bound and the upper bound is pretty big. I think it's a very interesting question to look at. Thank you very much. I ran out of time, so I'm happy to take any questions right now.
Thank you, Negev. So Negev can take questions. Negev, does this carry over? So this was for Levenshtein distance. Does this carry over to the weighted case?
What do you mean the weighted case?
Weighted eddy distance when you have like a cost matrix?
I'm sorry, I'm unfamiliar with this problem.
So you have different costs. You have different costs for matching different characters and.
Oh, I see. Okay, so it's not just either the same or different, but
Yeah.
there can be a distance. Well, let me think about that for a second. Yeah, sure. It should be okay because well, the first distance for one input to create the first distance oracle. Well, you simply output the distance using between any pair of input streams. So you just build a distance oracle for that, and everything else remains mostly the same. So I'm not too familiar with this problem, but it looks to me like from whatever you described, it should be obtainable in the same way.
Yeah, that would be nice. Other questions? There's
a question in the chat.
Yeah, there's a question in the
sorry,
chat from
I don't know how. Oh, yeah, I see.
Do you get something new also for longest common subsequence?
Yeah, that's a great question. We did not get anything for the longest common subsequence, but we have thought about it a bit, and we believe that we can get a similar result. So we believe that with sufficient work, it should be possible, and I think it would be interesting direction for someone to extend the work for the LCS. Basically, to do that, one would need to, instead of using triangle inequality, the LCS cannot guarantee. We need to use something that we call a triangle inequality on average. So if the number of string in an interval, or the number of interval, right? If you take one distance oracle, and each one of the string of length W only can have at most n to the epsilon degrees of freedom, then if there is sufficiently many comparisons, they will satisfy something close to triangle inequality on average. But the guarantee will not be constant approximation. It will be something like polynomial approximation, I think, because the distance there is, the distances are more subtle. So I think there was a subquadratic algorithm by, if I believe, Aviad Rubinstein. I said there was some work in that direction, and I believe that our techniques might be applicable to get this down all the way to 1+2 and to the near linear time with similar approximation that they got.
Okay, we're out of time, so thank you again. And again, if you can stop sharing your screen.
Absolutely.
Dominique can set up for his talk.
Thank you.
Can you hear me?
Yes, we can hear you well.
Can you see the slide?
Yes, and it's full screen, so okay. This is all, I think you're ready to go. So the next talk is by Dominique Kempa. Dominique, please.
Okay, thank you. See that? Okay, let me start. Okay, hello everyone. This is joint work with Tomasz Kociumaka. So as a motivation for this research, consider the following problem. The 100,000 Human Genome Project is a research project that involves obtaining a complete genome of 100,000 people to study genetic diseases. And this project has recently been finished, and since a human genome consists of about 3.2 billion symbols, the size of this dataset, assuming each symbol is encoded using 2 bits, is around 75 terabytes. One of the most basic queries on such dataset asks to count or list all occurrences of a given short pattern. And due to sheer volume of data, any solution that involves repeated scanning of it is too slow. Similarly, solutions based on batching the queries are not satisfactory. What we are after is the ability to answer queries online. And the crucial observation that allows us to efficiently handle this dataset is that genomes of 2 people are nearly identical. So by compression, we can thus reduce the size of the data by orders of magnitude. The standard compressed representation, however, is not searchable. And the solution to this problem is a data structure called compressed index. It allows performing queries over the original text T in space close to the compressed size of T. We can think of this as a searchable compression format. By adding the searching feature, the size of the compressed file grows slightly, but the resulting file is still orders of magnitude smaller than the original data. It basically grows by logarithmic factors. And in order to understand the space usage of these data structures, we need to understand the theory of the underlying compression methods. And we are particularly interested in understanding how different compression methods compare to each other. So to define the problem tackled in our paper, let us thus take a closer look at the 3 main compression algorithms, lossless compression algorithms. These 3 methods together account for about 94% of existing compressors. So let's begin with statistical compression. It is based on encoding symbols using varying number of bits based on the computed or predicted symbol frequencies. In the limit, these methods approach the kth order entropy of the text. Thus, they are well suited for inputs that have very highly skewed symbol frequencies. The drawback of these methods, however, is that the entropy is not sensitive to repetition. If we concatenate T copies of text, the output size essentially grows by a factor of T. The main idea in lamp-positive compression is to explicitly locate repeating substrings in the input. Each of the repeating substrings is encoded in constant space as a pointer to the previous occurrence. LZ compression is therefore particularly suitable for inputs with many repeated substrings. And these 2 compression methods are thus fairly well understood from the theoretical point of view. Namely, it is clear what kind of redundancy they remove. So BWT compression, on the other hand, is known to compress somewhere close to LZ77, but fairly little is understood about how it exactly relates to LZ77. So in contrast to the other 2 methods, BWT is thus relatively poorly understood. So with that in mind, we ask the question, what is the output size of Burrows-Wheeler compression? The following was known about the relations between output sizes of these 3 compression methods. Let Z denote the output size of the LZ77 compression, R the output size of run-length BWT, and by S we denote the output size of statistical compression, which is essentially the kth order entropy times the length of the text. So the following was known until now. The first result is by Manzini, who showed that Burrows-Wheeler compression can be bounded by the size of statistical compression. And the second result is due to Geigi et al., who proved that lamp-positive compression is bounded up to log factors by Burrows-Wheeler compression. In other words, we therefore know that BWT is somewhere between LZ and entropy compression. So we are now ready to state our results. Our first main result is that Burrows-Wheeler compression can be bounded up to log factors in terms of lamp-positive compression. So now we know they're essentially equivalent. So we really only have 2 compression methods rather than 3. This immediately implies a number of other results. For example, it proves that we can support powerful suffix array and suffix tree queries in space close to O of Z. It also implies optimal time algorithms for many problems on strings, assuming the input is weakly compressible by LZ77. And our second main result is the algorithm to convert between LZ77 compressed file and BWT compressed file running in time that is roughly proportional to the size of compressed file. And compared to the previous algorithms for this problem, ours achieves up to exponential speedup. And to achieve this, we introduce a number of new techniques of independent interest. So in this talk, I will focus only on the first main result. So let's formally define these two compression methods that we are looking at, which are LZ77 and Barrows-Wheeler compression. So let's start with LZ77. The key concept in LZ77 compression is the longest previous factor, or LPF. The LPF of I is the longest substring starting at position I that has another occurrence starting at some position j smaller than I. So let's look at the example here. At position I, the LPF has length 4, because that's the longest substring that starts at position I that occurs earlier. And we see that earlier occurrence at position j. And then the LZ77 compression is defined as follows. Given a string T of length n, we greedily, left to right, partition it into LPFs, or single symbols if the LPF length is 0, but that's a special case. And then once that partitioning is finished, we output the encoding of each LPF or a single symbol as a pair. And by Z, we denote the number of pairs in the output. So let's look at the example. Suppose we have already partitioned the string up to position 11. We then look at position 12, that's current I. We find that the LPF has length 3 and the earlier occurrence at position 7. So we output 3, 7 in the output. And then we continue at position 15. We do the same until we partition the whole string. And here we have 7 phrases, so Z is 7. Okay, so that's LZ77. Let's now define BWT compression. So let T be a string of length n, as before. We assume here that the last symbol of T is a special sentinel symbol denoted with $. That's a technical assumption. And then the Barrows-Wheeler compression is defined as follows. We start by lexicographically sorting all suffixes of the text, and we denote the starting position of the ith smallest suffix as SA of I. Then for any I between 1 and n, we define the BWT of I as the symbol preceding the lexicographically ith suffix of text. Formally, if SA of I is greater than 1, then the BWT of I is the symbol at position T of SA of I minus 1. And in the special case of suffix array having value 1, we define the BWT of I to be the $. Symbol. So the BWT of the example string looks like this. So it's just a sequence of symbols preceding lexicographically sorted suffixes. And it is easy to see that BWT is a permutation of the input string. And the important property is that it is an invertible transform. That is, given the BWT, we can restore the original string. So then the last step of BWT compression is to apply run length encoding on the BWT. That is, we represent every block of equal symbols, every maximal block of equal symbols, using a pair of integers, a pair containing a symbol and a run length. And by R, we denote the number of runs. So the runs for the BWT in the example look like this. And the corresponding encoding looks like this. I'm not sure if you can actually see it because it might be cutting off a little bit on the bottom, but anyway.
We can see.
Okay, okay. So there's 8 runs here, and therefore R is equal to 8. So we're now ready to present the sketch of the proof of the main result of our paper, namely that R is at most O of Z times log squared of n. So for any index I between 2 and n, we define the LCP of I to be the length of the longest common prefix between suffixes starting at position SA of I and SA of I minus 1. For completeness, we define LCP of 1 to be 0. So in this example, the LCP of 8 is equal to 3, since the corresponding 2 adjacent suffixes in the suffix array share a common prefix of length 3. And we call LCP of I irreducible if either I is equal to 1, that's a special case, or BWT of I is different from BWT I minus 1. In other words, irreducible LCPs are the LCPs between suffixes which are on the boundary of runs in BWT, and you can see it if you highlight the runs. So the following lemma holds: the sum of all irreducible LCPs having values in the interval from L to 2L, for any L, is bounded by O of ZL times log n. The complete proof of this lemma is in the long version of this talk. That's the one available on YouTube. And the proof is not very long, but it's a little too technical for a 10-minute talk. I would just say that it's based on the heavy path decomposition of the trie containing reversed substrings of length L. So you have to take a very specific thing to see. Now observe that the above lemma is all we need to prove our main result. First, recall that the number R of runs in the BWT is equal to the number of irreducible LCP values. And then the key trick is to classify all BWT runs into log n buckets based on the value of the corresponding irreducible LCP value. More precisely, we consider intervals of the form Li to 2Li, where Li is equal to 2 to the I for all I between 0 and log n. And this way, every irreducible LCP is accounted. The number of elements in a bucket is maximized when they are all as small as possible, but since they only differ by a multiplicative factor of 2, even if they are as small as possible, there can only be at most z log n of them in a single bucket. And to account for LCP values equal to 0, we observe that their number is bounded by the alphabet size, and the latter is no more than z, since there's at least one phrase for each different symbol in the text. So let me conclude. We have presented a sketch of a proof that the value of r is up to log factors bounded by the value of z, log squared to be precise. In the paper, we also described the first algorithm able to convert between LZ77 compressed text and BWT compressed text in time that's essentially proportional to the size of compressed data. And in addition to these main results, we obtained some auxiliary results that includes other bounds as well as new data structures. Future work includes proving the tightness of our bound, reducing the log factor in the runtime of our algorithms, and designing practical algorithms for converting between compressed representations. And that's it. Thank you for attending my talk.
Thank you very much for a nice talk. Are there any questions?
I would have a question.
Sure.
So you showed that these two compression methods are essentially equally long.
Mm-hmm.
But like I could have just used the other compression method, right? So why is it important? Can you maybe highlight this again?
Okay. So they all differ, like depending on which compression method you use. So our the key motivation was on the first slide, which are these compressed indexes. And so for each compression method that you choose, there are corresponding compressed indexes, and they differ in what kind of queries you can do, and what's the exactly by how many logs the space grows, but also you can argue about the runtime of queries is different. So the better the compression you use, the less the smaller the data set, but then the less powerful queries you can do. So it's not that it's all these compressions are the same. So essentially, our motivation for understanding the compression methods is to understand these data structures ultimately. So because now we know these two are equivalent up to log factors, then we know that we cannot, there's certain lower bounds that hold for them. And yeah, so to really answer your question is that by choosing which compression you use, you restrict yourself to only certain types of queries that you can do. And in order to understand these queries better, we want to understand the compression method, different compression methods.
So are there some queries? Sorry, maybe can I ask another question?
I think so.
So so you have data like these two different compression methods, and you say they support different queries.
Mm-hmm.
That obviously leads to the question, would you maybe want to invent a third method that has the best of two worlds and supports all types of queries? Or is that not needed or useful?
So in some sense, this is what this result is achieving, because it shows that they're actually equivalent up to log factors. It means that really it's really only one compression method. So the queries you're supporting, it's really the same thing. So yeah, it's a good question, and sort of in some sense we don't have to do it anymore, because we now know they are really the same. I mean, generally we don't care that much about log factors here, so you sort of get the best of those of the two this way.
Thank you.
Thank you, Dominique. Let's move on to the next talk. So Dominique, if you can stop sharing, and our next speaker, yeah, it's about time. Next speaker is Tilman Mitzo. Till, can you share your screen? Great, you can start.
You see my screen?
We do.
Okay, great. Let me just move you to the screen that I look at you. Thank you for coming to my talk. And maybe as a motivation, I want you, so this is about packing, I want you to show a very simple example. I like to look at these things that are very simple and we cannot solve. So here I have 11 unit squares and I want to pack them into a square. So these are like the simplest possible object that you could consider, squares, and into the simplest possible container, also a square. And the sad news is, while you see in the slide the best known packing, we don't know if there could be maybe an even smaller square container containing all of those 11 squares. So that I found a little bit fascinating. And so this talk gives an explanation on why we cannot, or why we're currently not able to solve that question. So let me introduce my collaborators. So this is Mikkel Abrahamsen from Copenhagen and Nadia Seifert from Free University of Berlin. Okay, so this is the problem we want to study today. We have given a bunch of items and we've given a container and we want to put all the items into the container. Okay, so there are, this is a also very practically relevant question. So for instance, if you look at factories where they cut out patterns to make sweaters, then for instance, you would have this big piece of fabric and you would arrange them so that you have as little waste as possible. Or also if you have some leather product that you're providing. And what you can see here is that in practice, we care for different types of shapes. So we may have, we may not have just translation, but sometimes translation is required. But we may have also containers here, for instance, these leather patterns, which are not square or rectangular containers. And also you may have non-polygonal shapes. So we want to study the packing problem where our containers and our items are of different categories. So the categories, simplest is unit squares, to arbitrary shapes for the pieces, and also for the containers, squares would be the simplest container, and arbitrary shapes or simply connected pieces would be shapes would be the most complicated containers. And what was known before we started working on this is that essentially all of these variants are NP-hard, and that is both when we allow rotations and when we do not allow rotations. And our contribution is to show that a big set of them is actually more difficult than NP-hard. They're actually complete for this complexity class called existential theory of the reals, which I will introduce in a minute. But yeah, just reiterating that already for 5 squares, the solution, the optimal solution is irrational. And yeah, for 11 squares, we don't know the optimal solution. Okay, so going back to the picture, these are our new contributions for rotations. And if there are just translations allowed, then we show that this set is ETR complete. And actually, it was already known, but we have not really found a source, but it was folklore, that these versions, the rotations are contained in NP. And as an exercise, you can think about why this is the case. You need to use LPs and get some order times. So what is this mysterious complexity class existential theory of the reals? So let's reiterate what is NP. I use now that you know what is NP, but the specific way of looking at NP is to say we have this crystal ball and we find a solution, and then on a word RAM we verify that that solution is correct. And now we do the same with, we define ETR in exactly the same way. We look in this crystal ball and we get a solution, but now the solution can contain real numbers. And then we check that the solution is correct on the real RAM, which is like an extension of the word RAM, but you allow to manipulate real numbers. So it's really an analog to NP. From the complexity point of view, this complexity class ETR is between NP and P space. It's trivially containing NP because just the real RAM is more powerful than the word RAM. And it was a result by first Kenny, who showed that ETR is contained in the complexity class P space. Here are some example problems. So for instance, there was today a talk, no, not today, but at FOCS it talks about the crossing number. So minimizing the crossing number is ETR complete, somewhat surprisingly. If I give you a graph and ask you, can you recognize this at disk intersection graph, that's also ETR complete. So here for every disk we represent a vertex, and vertices are adjacent if and only if the corresponding disks are intersecting. Okay, this is a pseudo-line stretchability important problem in geometry and the art gallery problem. So what I want to say here with all these examples, what you see is that complexity class is particularly important for the area of computational geometry. So many of the problems which are complete for this class turn out to be geometric. So you now know about some of those problems. So there's an argument that is often made, which is, okay, I already know the problem's NP hard. So why do I care that it's even harder than NP hard? And so there are different reasons for this. One is you're just curious, but maybe for the algorithm designer, they often use tools that they have, right? They use FPT, they use SAT solvers, they use IP solvers, and they try to do this. And they will all fail because if you could use any of those methods, then you would show NP equals ETR, and that's not known. Or that would be a big breakthrough because lots of problems are not known to be that are ETR complete. We don't believe, or we think they're not in NP. Okay, that was it. So my collaborators again, Mikkel Abrahamsen from Copenhagen and Nadia Seifert from Berlin. And I think I'm one of the few speakers who are below the 10-minute threshold.
Thank you, Theo. Any questions?
So you were talking about showing that a subset of all these problems was ETR complete. So another subset remains. Do you have any ideas of whether they may be ETR complete or not?
You mean here? Yes.
Yes.
So with Rainier, who is also in the audience, he's one of my master students. We have some ideas that we develop, and we try to show that these problems are also ETR complete, but it may take another half a year. So maybe, yeah. But there's some belief that maybe we can show that those. Can you see my mouse? Yes. Those problems are ETR complete. But for those we thought about, and they may lie in some other complexity class, because here we can encode concave constraints, but not convex constraints. And we believe that for ETR completeness, you may need to have convex and concave constraints. For NP hardness, concave constraints are enough. But yeah, we have some intuition that maybe concave constraints alone are not enough. Thank you for the question.
It's also a question on the chat. Does the following conjecture make sense to you? Under the assumption of the exponential time hypothesis, does it make sense that the polynomial hierarchy is containing ETR containing P-space? Strictly.
I don't think that we know any relation between ETR and the polynomial time hierarchy. Yeah, so and I don't think that ETH would help to show any relation there, but yeah, I would not know how to show such a statement.
Another question on the chat, is the generalization to 3D harder, even harder than the 2D case?
No, it's also ETR complete. So because of this definition here, you know that it's contained in ETR. And then every two-dimensional object, you kind of, you do that, right? And does that make sense? Okay. You just take a Cartesian product with the units interval.
Mm-hmm.
Or you do that. Yeah. And then it's their equivalent, the 2D and the 3D example, because it doesn't make sense to rotate in the third dimension. You're only allowed to rotate in 2 dimensions. Because the container is lifted, you take the 2-dimensional container, cross it with the unit square,
mm-hmm.
and then you get a 3-dimensional container with the unit interval. But it will not help you to use that, because all your pieces are also you take also the Cartesian product with the unit interval.
Another question: how do you show ETR hardness? What is the canonical complete problem for ETR?
Yeah, so we show ETR hardness from a restricted version, which is called ETRinf. So usually, if you want to show ETR hardness, you have to show addition and multiplication. And now we have to show only addition, and you have to show the constraint x times y equals to 1. So we have also some extra promises there, which we use, namely that we know that each variable is in an extremely small range. Something like you could imagine that in NP time you could already guess the range of each variable, and this range will be something in the order of magnitude of n to the minus 300. In that way, we almost exactly know how everything is packed, and just that teeny tiny movement is unknown. Thanks for the question.
Answer your question? Yes, it does. Any other questions?
I was wondering if it's hard still to just approximate the optimal packing.
Yeah, so I guess if you have just one piece less, right, then you make some error. But I mean, there are people who do show APX hardness for all types of packing problems. And I guess then you would easily fall into NP, right? If you allow to just remove some pieces. So I don't think that would be ETR complete to approximate.
Okay, any other questions? If not, let's thank Till again. I think it was a very graphic and nice presentation. Thank you.
Thank you. Thank you.
The next talk will be given by Ivo van der Hoog. I hope I pronounce your name correctly.
Yeah.
Okay, let's wait a few more seconds. In case someone wants to join just in time. Okay, I think we can start. So, Ivo, please.
So welcome to the short talk about smoothing the gap between NP and ER. This is joint work between Jeff Erickson, myself, and Tilman Milsa, who you just saw. Now, before I can explain anything about the results, I first need to explain something about computation in general. Now, most of you are probably familiar with the word RAM. It's a model of computation that we use, where we imagine that the memory of a computer is basically an array, where in each cell you can store a value up to W bits. Then we imagine that we can do some sort of a constant time manipulation. This includes things like addition, comparison, maybe bit shifts, and we usually find that this model matches the reality of a real computer pretty well. Now, in computational geometry, they often use another model, which is called the real RAM, where we assume that in each memory cell, we can store a real value up to infinite complexity. And we can still do things like constant time addition, comparison, and all sorts of things. Now, this is very nice if you're working in a geometric setting, because there it's very easy to generate values that need very high precision. For instance, if you reason about the circumference of a circle, then pi is bound to show up. And in this model, you can just reason about working with pi without wondering about how much precision you need, and you can then focus on the steps your algorithm needs, and that's how you do analysis. A downside of this model is that it's often called unrealistic because it sort of assumes an infinite precision that in reality is not there. Now, these two classes also come with complexity classes, and the word round has a very well-known one, which is called the class NP. We all know that it comes from the set problem, which is basically the following problem. I give you a logical formula of Boolean variables, and you look for an assignment of Booleans such that the formula rings true. Now, we call a problem NP hard whenever it's as difficult as set, and we say that a problem lies in NP if it can be written as a set formula. Now, the real RAM has a complexity class, which Till just talked about, which looks very much like NP. It comes from the problem ETR, where the input is a formula of real variables. Now, we look for an assignment of reals such that the formula rings true. A problem is hard for the existential theory of the reals when it's as difficult as ETR. It lies in the existential theory of the reals if it can be written as an ETR formula. And whenever we are confronted with these two classes, we can wonder what is actually the difference between these two. And what that basically means is, well, whenever you have one of these real valued problems, what happens when you try to run it on a word RAM? What happens if you even try to put the solution in a word RAM? And Jiří Matušek had the following to say about this. Serious people seriously conjectured that the number of bits can be polynomially bounded, but it cannot. And what he was talking about is a phenomenon that appears to be a gap between these two complexity classes. And specifically, it could be an example like the following. So here you see the art gallery problem, where the input is a simple polygon, and we want to place a collection of guards such that the guards together see the entire polygon. So every point, there's a line of sight to at least one guard. And we know that there's a worst case example, for instance, this one, where the bit complexity needed to represent the guard locations is exponential or more. And what we mean by this is there is an input which can be specified with integer values, such that the optimal solution needs to be specified with reals. And this sort of creates a gap between the two complexity classes, because it's very hard to then show that this problem would lie in NP, because how could you encode its solution as a polynomial size NP formula if the solution may or may not be decoded using only polynomial size? And this is what we're confronted with. So we see this complexity class, and we know that NP hard problems are existential hard for the existential theory of the reals, but somehow we have no way of placing these existential R complete problems in NP, at least no obvious way. Now, we try to bridge this gap, and we do it intuitively, basically in two ways. First, I'm going to talk about the behavior of these two complexity classes, and we're going to reason about a Cook-Levin-esque theorem. And then I will explain smoothed analysis, which will be our main tool for trying to bridge this gap, and then I can state one of our theorems. So let's go back to these classes. Earlier, I was talking about this idea that you're in NP if the program or the algorithmic problem can be written as a set formula. However, this is not how we usually reason about problems that lie in NP. Right? Usually, we say that a problem lies in NP if and only if it has a polynomial time verification algorithm. And this is the famous Cook-Levin result. And that basically means if I give you a solution, I ask you, can you check for me in polynomial time if this solution is correct? If you can always do this, then this problem lies in NP. And it's a very intuitive way of thinking about the complexity class NP. Now, there is no such statement yet for the class ETR. And it sort of means that it's kind of hard to show that problems lie in the existential theory of the reals. So what we want to do is want a way to transform a real RAM computer program, a polynomial time verification algorithm in the real RAM, into an ETR formula. But before we can do this, we first revisit the definition of the real RAM. So we look at common, well-known definitions, and we reason about what basically the real RAM should and should not be able to do. And what we explain is that you can sort of view the real RAM, in our opinion, as an extension of the word RAM. So you just have a CPU, which has word registers and real registers, and it has access to certain operations on both. And we reason about which operations are and are not reasonable, safe, etc., etc. And given this toolbox, we can show a Cook-Levin-esque result, which indeed says that, okay, if you give me a verification algorithm on the real RAM, that on the real RAM runs in polynomial time for an algorithm problem, then that problem lies in the existential theory of the reals. And the result of this is that then this now gives an easy membership proof. We just saw Tails talk earlier. You can wonder about, well, does the packing problem lie in ETR? Well, if I give you a packing, surely you can find a way, to in polynomial time in the real RAM to check if this is actually a valid packing and if no things overlap and if it's in within the container, etc., etc. So that's very nice. But then we still have this gap. But there's some interesting phenomenon going on with this gap. You see, we had an example where in the worst case, we would need an optimal solution that would require massive bit complexity, which would make it very hard to place it in MP. But we know that in the average case, this is not necessarily true. So suppose I were to give you a random polygon for whatever definition of random you might find convenient, then what is sort of intuitively known is that the bit complexity you would need to represent the optimal solution is logarithmic. And hence it's very easy to make then a polynomial time verification algorithm if you were to translate things into the word RAM. So we know that worst case, we have something that might indicate a gap, but average case, it doesn't. Now we go a step further by using well-known smoothed analysis results. Now, smoothed analysis works as following. You look at a specific instance, or you take the maximum overall instances, say our worst case instance that we saw earlier. And what we do is we permute it by at most delta. So in this case, what you could think of, you can grab every vertex and you can move it a random direction and a random distance somewhere between 0 and delta to obtain a new polygon. And what smoothed analysis does, it looks at the complexity in this new permuted world. So you can look at the expected complexity after such a permutation delta. So this delta interpolates between average case and worst case, because the smaller delta gets, the closer and closer and closer you go to worst case analysis. Now what we want is we want to reason about smoothed bit complexity. So what is the bit complexity you need after such a permutation? And what we do for this is we basically we define real RAM algorithms, and we want to see what happens if we take this permuted input, make it integer, and run it on a word RAM machine. Now, in order to do this, we again need to revisit our real RAM definition, and we need to reason about what does it mean to translate input, right? What does it mean to go from reals to integers? And you need to reason about what does it mean to go from real RAM instructions to word RAM instructions. But when you do this, and you can see this in the paper and in the longer version, you get the following result. We show that for a very large class of ETR complete problems, their optimal solution can be represented with practically logarithmic bit precision, where practically is being defined as, well, you expect the bit precision to be needed to be logarithmic in n over delta. So for very close but constant delta, it would in fact be logarithmic. And the consequence is that these ETR complete problems, they practically, for most inputs or for most input apart from some very degenerate instances, lie in MP. And it shows that if there is a boundary between these two complexity classes, it must be made up by some very contrived input, as it were. Now, this is our short talk. If you want to know more, you can watch the long video or read the paper. And thank you very much for listening.
Thank you, Ivo, for a nice talk. See, there's a question on the chat.
I cannot see the chat right now.
So let me read this. In polyhedral optimization, if the problem satisfies totally dual integral property, for example, matching polytope, its linear programming formulation can give the optimal integer solution. would this property be useful to bridge the NP and ETR gap?
This is a very good question. So the attentive listener indeed said, listen here, that every time I said, this appears to make a gap. And that's because it's not clear that these solutions that you saw, even to the art gallery problem, really need infinite precision, right? We know that they need infinite size coordinates, but what we don't know is that there might not be a smarter way to represent the solution and to use that for some sort of a polynomial time verification algorithm. So yes, this is a very good question, and I think it's why the gap between P and NP is not really that known.
Okay, thank you. Any other questions? Okay, so thank you again, Ivo.
Okay.
We have a few minutes until the next and last talk of the session. The talk will be given by Max, right?
Yeah.
So Max, if you'd like, you can also already share your screen.
Sure. Can you see?
Yeah, we can see it properly.
Okay, great.
Good. Okay, we'll start in a couple of minutes. Okay, the last talk of the session will be given by Max Hopkins. Max, please.
Thanks. Hi, I'll be talking about solving the point location problem in active learning half spaces almost optimally based on joint work with Daniel Payne, Shachar Levitz, and Gaurav Mahajan. So to start off, I want to talk about what is the point location problem. Well, given a known set of hyperplanes, usually called a hyperplane arrangement, that partitions R to the D into cells, and an unknown point X somewhere in R to the D, we'd like to figure out which cell of the hyperplane arrangement contains X. Now, of course, with no information about X, this isn't possible. So we'll be given access to X through what are called linear queries. Essentially, for any hyperplane H in R to the D, we're allowed to ask whether the unknown point lies below that hyperplane or above the hyperplane. So let's take a look at a quick example to get a better idea. Down here, we have a very basic hyperplane arrangement in 2 dimensions, and we have an unknown point highlighted in red. Now we're allowed to pick hyperplanes and ask, does the point lie below the hyperplane or above the hyperplane? So here I picked one in our arrangement, and I would get that the point lies below this hyperplane. I could also query hyperplanes not in our arrangement. I could pick this one going down the middle, and I'd get it to the right. And I can keep making more and more queries until eventually I get enough information that I figured out that this point has to lie in the center cell. And here I made 4 queries, and the overall goal is to make as few queries as possible to find the correct cell. So I want to take a moment to talk about the dual view of this problem, which actually comes from more of a learning theoretic standpoint. So instead of a set of known hyperplanes, here we'll have a set of known points, like data points in d dimensions, and our input will be an unknown, and for now we'll assume homogeneous hyperplane in R to the d, which is just like a linear classifier. And the goal in this dual version of point location is to learn the labels of all the points in X with respect to that linear classifier. And the goal is to do this in as few queries as possible, where in this case, a query is asking for the label of some point in R to the d, whether it's above or below the hidden hyperplane. And again, this could be the label of a point actually in our set X, or we could kind of make up a point. We could synthesize data and ask whether it lies above or below the classifier. Okay, so our goal is for an arbitrary point set X in d dimensions of size n. We'd like to know how many queries it takes to find the labels of all the points in X. So let's talk about some naive bounds for this problem. Well, certainly you can do this in n queries, where n is the size of X. I could just ask for the label of every point in X. Surely that would solve the problem. But that's not very good. So what's the lower bound? Well, there's an information theoretic lower bound that's exponentially smaller, of d log n, where d is the dimension that our point set lies in. And the way to see this lower bound is that if there exist arrangements of n points where passing hyperplanes through them in different ways gives you about n to the d possible labelings. And because our queries are binary in nature, it takes at least log of this number to even differentiate between the different possible labelings, and log n to the d gives you the d log n lower bound. And the big open problem in point location for the past 40 or so years has been whether this lower bound can be matched. We've certainly known that you can do better than n, better than the trivial solution, but whether d log n is the correct complexity for point location has remained open for a long time. Okay, so before telling you about that, I want to give a little bit of motivation for this problem, actually from the machine learning standpoint. So most current machine learning algorithms in practice, like deep learning, require massive amounts of labeled data. Whereas what we usually have access to in practice are massive amounts of unlabeled data online, like pictures on Instagram, we see millions every day, tweets on Twitter, posts on Facebook, etc. But labeling this data can be really expensive because it actually requires querying humans, either crowdsourcing or even experts in some cases. And this has actually birthed like an entire subfield of learning called active learning, which is in opposition to maybe what would be more standardly called passive learning, or what you'd think of as pack learning, where the learning algorithm receives a stream or a batch of labeled examples. And the goal is to ask how many labeled examples do you need until you can kind of learn all the points or approximately learn your classifier. The active learning model, on the other hand, the learner will receive a big batch of unlabeled examples, more like what you'd have access to today, along with an oracle, like a human annotator, that it can query to get labels for these examples. And the idea here, the goal is that by kind of cleverly picking points, adaptively picking points to send to the oracle, you can end up using many fewer labels to still kind of learn all your points or get enough to run whatever your desired algorithm is. So you might notice that this active learning model is very similar to the dual version of point location that I was talking about before with respect to the class of half spaces, except the main difference is that in point location, I was allowing you to query any point in R to the d, not just something in the data set that you were given. This is actually well studied in active learning. It's called membership query synthesis. And I want to take a little bit to motivate this, because if you could get away with just sending real data to your annotators instead of kind of synthesized data, that would probably be better in practice. So I want to justify why we allow synthesizing queries. And in particular, it's been known for a long time that if you can't synthesize queries, even very basic classes like half space in 2 dimensions, you basically can't do anything better than the trivial algorithm asymptotically. You pretty much have to query every point. And to see an example of this, you can just imagine your data is laid out in a circle, like in the image here, and the adversary picks 1 point to cut off. And basically, you can't do anything better than just query all the points to find the point that got cut off. On the other hand, if you are allowed to kind of make up data to send to the Oracle, if you have membership query synthesis, we've known for a long time that you can basically recover binary search. You can do exponentially better. You can learn everything in only O of log n queries. And this is because these red points here, which aren't part of our data set, but are still in 2 dimensions here, are much more informative about where the hyperplane that we're looking for actually lies. And point location viewed in this setup basically asks, how does this result scale into higher dimensions? We know in constant dimension that looks like O of log n. How does this scale with D? And there's been a lot of work on this in the past 40 or so years, and we've essentially known that the answer should be poly d times log n, and the goal has been to get this down to the information theoretic lower bound of d log n. Prior to this work, the best known solution for arbitrary point sets was a work from Ezra and Sharir that gave a d squared log algorithm. And finally, in this work, we very nearly reached the information theoretic lower bound of d log n, where we're off by an additive subpolynomial factor in D that I'll talk about in a bit more detail in a second. Okay, so I want to now jump into actually what our results say in more detail. We actually study 2 regimes for this problem. The first one is more from a learning theoretic standpoint. It's the high probability regime. So given an arbitrary set x in d dimensions of size n, we argue that you can label all of x with probability 1 minus delta in about d log n over delta queries. So this is very, very close to the information theoretical optimum. And moreover, you can actually plug this into your favorite pack learner, and it shows that you can actively pack learn half spaces as long as you're allowed to synthesize points with membership queries in about d log 1 over epsilon delta queries, which is again very close to the information theoretical optimum and is a factor of d better than any previously known algorithm to our knowledge. The second regime we study is much harder. It's the zero error regime, and this is more common to computational geometry. So in this regime, again, given an arbitrary point set x in d dimensions of size n, we claim that we can label all of x in about d log n plus d to the 1 plus little o of 1 expected queries. So I want to make a couple points here. The first is that we've relaxed our complexity measure. So we now look at expected queries instead of worst case number of queries because the zero error regime is much harder. The second is I want to talk about these 2 terms here, the blue term and the red term. The first term actually pretty much comes from the previous theorem. The idea is that we're first going to learn x with high probability, and we might allow errors. And this is basically optimal. And the second term comes from a complicated verification process where we basically go into our probabilistic learner manually, and we verify that we didn't make any mistakes along the way. And this is complicated. It relies on the internal structure of our learner. And we think that this is one of the main areas left for improvement, where we hope that there's some simpler, maybe geometric way to verify probabilistic solutions that'll actually be closer to the information theoretic lower bound, instead of being off by this d to little o of 1 factor, which is about 2 to the root log d. Okay, so that's our results. I want to spend a minute or 2 talking about what our algorithm actually is. So our algorithm is based off of kind of a standard strategy in machine learning called learning high margin points. So the margin of a point just measures how far away it is from the hyperplane, and it's kind of long been known that learning points which are far away from your classifier is much easier than learning points which are like close to the boundary. So our algorithm will proceed in rounds, and in each round we're going to try to apply this weak learner in some way. So the first thing that we need to do is we need to make sure there actually are high margin points. If there are no high margin points in x, we can't learn anything. So what we'll do is that we'll rescale x into some kind of nice symmetric position called approximate isotropic position. And the idea with doing this is that it scales the margin. It gives some kind of nice structure to the margin of the points, but it doesn't change the labels of the points. So you don't have to worry about making mistakes after you do this scaling. And what we'll do second is we'll analyze kind of the fine-grained margin structure of our rescaled points. And in particular, what I mean by this is that we prove that you can efficiently find a parameter ki somewhere between 1 and the dimension d, where a ki over d fraction of the points have large margin, and most of the remaining points have very small margin. Okay, so a priori, it's not clear why I would care about these small margin points. I've said that what our learner does is it learns the large margin points. Well, the reason is that if you try to just naively apply the weak learner at this step, you might only be learning a 1 over d fraction of x in each round, and it would take d queries to do this. So this would end up taking d squared log n queries overall, which is good, but it's not close to the information theoretic lower bound, which is our goal. So what these small margin points allow us to do is actually to apply dimensionality reduction. And in particular, our strategy will be to project onto the orthogonal complement of the approximate span of the small margin points. And doing this largely leaves the margin unaffected, and it reduces to O of Ki dimensions, where Ki is this factor where we're promised that we have a Ki over d fraction of large margin points. So now if we kind of naively apply this weak learner for large margin points on the dimension reduced problem, each round will learn a Ki over d fraction of the points, but we'll only use O of Ki queries. And because we can do this for an arbitrary point set, we can just remove whatever points we learned, and we can repeat the process until we've learned everything. And because of the way that we've coupled the number of queries we make to the fraction of x that we learn, it's not too hard to show through a boosting argument that this only ends up taking about d log n queries. So I think I'm out of time. Thanks for listening.
Thank you very much for the talk. Are there any questions?
I have a question.
Sure, go ahead.
So can you go a slide back, please?
Mm-hmm. Oh, yes.
So you say you do dimension reduction, but earlier you promised me that you would only have access using these queries, what they're called, dot products that you take.
Yeah.
But now suddenly you do them like you simulate it, I guess, in some way.
Yeah. So it's everything is, we are kind of switching spaces and we'll restrict to subspaces, but everything is simulated over R and D. So you don't actually, yeah, you just simulate everything.
Can I ask another question?
Sure.
So, I mean, the problem that you described is a real problem, right? Like, if I go to these NLP people in my department, then they go to Amazon Mechanical Turk, and then they spend a huge amount of money to get these things labeled. But I mean, their restrictions are not nice hyperplanes, right? Like, no one expects this. So is there anything that you can tell them that how you're useful to them, or?
Yeah, it's a good question. I mean, the theory here is kind of far behind practice, unfortunately. And we're still kind of at figuring out how to do these basic classifiers. There are some things you can do, like trying to embed your classifier into higher dimensions as linear, right? Which is a common technique in machine learning. And then you can try to simulate things in higher dimensions for like a polynomial threshold function or something like that, but it won't be as efficient. But yeah, it's a good question. I mean, the theory is still kind of behind practice, unfortunately.
So related to that, maybe I missed it. How do you basically generate these queries? I mean, in the geometric setting, it's okay, but if they're actually points like images or something, you have to synthesize images or something like that, right? Am I mistaken in?
Right. So how do you generate these synthesized points? Yeah, it's a good question. So I guess there's a lot of literature on kind of membership query synthesis in active learning. And it's definitely true that in kind of cases like like classifying cats and dogs or something, a synthesized image that's half cat, half dog is not very helpful. Like a human annotator isn't going to be able to solve it. There are some things with like generating images with GANs, I think.
Yeah.
And I think kind of what's believed is the more useful case for this type of work is in like simulated science experiments where it's not actually a human annotator, but where you're trying to figure out maybe like what's the most useful experiments to run at any given point. Where like you don't have to worry about synthesized queries looking really weird.
Okay, thank you.
Is there time for another question?
Yes, there is.
So you said this previous work had some assumption, some structural assumption, right?
Oh,
that you now removed, like that's your contribution, that you removed that structural assumption.
You mean the Kane, Levitt, Moran, and Zhang work?
Yes.
Right. So their work assumes either that you have margin or bit complexity. So you have to like they run in like if your margin is eta or something, they run in like d log 1 or eta log n or something like that. So we remove any assumption. It's your point set can be as degenerate as you want.
So the one assumption is margin. That's a geometric assumption, I assume.
Yeah. So okay, technically they assume minimal ratio, which is basically bounding how close and how far the points are allowed to be from the hyperplane.
The spread, okay. And the other assumption would be bit complexity. Can you say
Bounded
something
bit
about that?
complexity. So you could do like grids. We already knew you could do like grids in D log n.
I see. So assuming that
early-
everything would lie on a grid, essentially.
Yeah.
And that grid is not too large.
Yes. Well, actually, it should. Yeah. Okay. I guess the bit complexity grows with how large the grid is. So yeah, sure.
Okay, thank you.
Okay, thank you very much. And let's thank again all the speakers of this session.
Oh yeah, and all hanging out at Gather, I guess.
Yep. And also the business meeting is in 30 minutes for those of you who are interested. Thank you everybody for joining this session, and bye-bye.